video, we're going to talk some more about forced motion. So we looked at that in the last video. We talked about the basic differential equation for forced motion. So I'm going to zoom back in on that. So we had the basic spring mass model for the left side of the differential equation, and then the forcing function is that external force applied to the system that's on the right side of the differential equation. And we last time looked at what happens when there is no damping, when C is equal to 0. And so for this video, we're going to look at what happens when we do have damping, when C is not equal to 0. All right, so remember that our basic model is my double prime plus cy prime plus ky equals our forcing function. And then we'll probably have an initial position and initial velocity. All right, and remember that m, c, and k will all be positive numbers. And so when I solve, I'm probably going to use quadratic formula and solve my characteristic polynomial. And so I'll get r values, and I'll just write down here in terms of m, c, and k what those would be from quadratic formula. So you would have negative c, the coefficient of the middle term, plus or minus the square root of c squared minus 4mk all over 2m. And you know from solving quadratic equations that the kinds of solutions that you get to quadratic equations depends on what is happening inside that radical. So one situation might be if that expression inside the radical, that c squared minus 4mk, is positive, then you're going to end up with two distinct real roots. And so that's what's listed here in our first possibility. If I get c squared minus 4mk to be greater than 0, then I'm going to get two distinct real roots. So r1 and r2 will be real numbers, both less than 0, and they'll be different from each other. So distinct real r values for that characteristic polynomial. And that ends up being what we call an overdamped system. Notice there's no trig functions in the result up for the YH. And so I don't really have any oscillations. I just end up with all of that YH approaching 0. Again, remembering that those R values are both going to be negative. And then if c squared minus 4mk is negative, you're going to end up with non-real values for your characteristic polynomial. And so that's when we get those trig functions like we have in this last step here. So c squared minus 4mk less than 0, we will have an underdamped system. We have those continuing oscillations that go on, but the amplitude decreases over time. And then kind of the other possibility, we either have the expression under the radical being positive or negative or neither. So really the bifurcation value there. If c squared minus 4mk is exactly equal to 0, we get repeated real solutions for our characteristic polynomial, and that's what we call a critically damped system. And so none of that part is really new, but just kind of a review. But the key part for all of that is that if we have damping, all of these YHs will approach 0 as t grows. And that's what it talks about in that next little paragraph right there. The negative coefficient of t in those exponential functions causes all of those YHs to approach 0 as t gets larger. So over time, the YH part of your solution is going to die out, or approach 0 or become negligible. For this reason, we call the YH in this situation the transient solution. This is important vocabulary, so you will need to know that vocabulary. What part of this solution is the transient solution and why it's called the transient solution. So that transient solution is the YH, and it's called transient because it doesn't last very long. It goes away as t gets larger. All right, and so if we think about when I have a non-homogeneous differential equation, like I have up there at the top, where our solution is going to be made up of two parts. So our solution is going to be y equals YH plus YP. So the YH is what we just talked about here. That comes from your characteristic polynomial. And in this kind of application anyway, the YHs will always die out. The YP then maybe is left, depending on what that yp is like. So that's what it talks about next. Since the YH dies out, the overall solution is going to approach the YP. And that's what this notation here means. The overall solution Y is going to approach the YP, the particular solution. So that YP is the part of the solution that is induced by that forcing function. It's important to understand that the YP is not equal to the forcing function because there are other forces in the system, but the YP is the part of solution that gets generated by that external forcing function being applied to the spring mass system that we have. All right, next, at the bottom of this page in your notes, there is a picture here that's important. And so there's kind of a lot going on here, so I want you to just kind of take a minute to pay attention to that. There's several different curves on here. So I'm going to talk about them in different pieces here. So we have the complete solution. So this would be the overall solution to the differential equation. And so that would be the curve that describes the motion of the object. And that is the thick black curve on this graph. And then I've also graphed on this graph the two kind of parts of that solution. So you can sort of see what happens there. If I just graph the YP, which is not really a solution, but what I want you to notice is that if I just graph the YP, eventually at about right around there, the overall solution, the Y and the YP, become nearly indistinguishable. And so one of the important parts on this picture here is illustrating that eventually the Y is approaching the YP as t gets larger. The other part that's important here, the thinner black curve, is that transient solution, YH, and you can see that that function has an impact on the overall solution at the beginning, but at about the same time where the Y and the YP become indistinguishable, that YH gets so close to 0 that you really almost can't even see it anymore. So if you kind of follow that curve that's labeled YH, at about that same time, that YH becomes so close to 0 that you can't even really see that on the graph. So this YH here is approaching 0, that transient solution. And in the case where YP is a periodic function, we call that a steady periodic function, or it is also sometimes called a steady state solution. So steady state or steady periodic. We will look later at some different kinds of forcing functions that are maybe not periodic and maybe not steady, and so we might call them something different a little bit later, but the important part there is that that YP is what is induced on the system from the forcing function. All right, in the next video, we are going to look at an example where we solve a spring mass problem that has a solution that turns out like this, so be sure to watch that.